So now we go to problem number 7, which is another classic, and that has plane geometry. So we have now done spherical geometry, we have done cylindrical geometry, and now we do plane geometry. Here is a plane which is infinitely large in size. X equals 0 here, x equals plus d, and x equals minus d. And we have a charge density here, rho coulombs per cubic meters. So it's uniformly distributed throughout density rho coulombs per cubic meter, and you're being asked what is the electric field here, here, and there. Well, let me do the electric field outside, and let me leave you largely with the electric field inside. I choose here a cylinder, but it doesn't have to be a cylinder. It could be a box like this. So I don't want to mislead you on the cylinder, but I choose a cylinder. And the cylinder sticks all the way through this slab. And here is the bottom of the cylinder. And it is crucial, essential, and an absolute must that this distance here above the slab must be the same as the distance below the slab. And you will see shortly why that is. So the charge inside this cylinder is the charge which is only here. For reasons of symmetry, the electric field could only be pointing radially outwards, or I shouldn't say radially, could only be perpendicular to this surface, because nature could not decide between left and right. So the E vector must be like here. And the E vector here must be also perpendicular to this flat surface. But since I have chosen this H the same, this E must be the same as that E. If you choose this H different from this H, you have no knowledge yet that those two E vectors are the same. Turns out that they are the same, but you don't know that yet. So you must choose this H the same as this H. Only then can you justify saying that the magnitude of the E vector here is the same as the magnitude of the E vector there. The DS's are pointing outwards, so they are here parallel to E, and the DS's here are also parallel to E. So both here and here are the cosine of the angle between ds and E plus 1. What now is the electric flux that is escaping from this cylinder? And you could have taken a box. Well, the electric flux escaping here is the same as the electric flux escaping here, because ds and E have the same, are both in the same direction. So I get A times E. If A is this surface area, but I have two surfaces, so I have a 2, and that now equals the charge inside. Well, maybe I am forgetting something. How about the flux escaping from the sides? How about the flux escaping from the cylindrical surface? Well, that flux is 0, for the reason that ds everywhere on the surface of this cylinder, and even if you had chosen this box, everywhere on these vertical surfaces, ds and E would be perpendicular to each other. The dot product would therefore be 0. So there is no contribution, there is no electric flux coming out from the cylindrical sides. No contribution from the vertical parts of the box. Only from the two end pieces. And so I can indeed now say this must be the total charge inside. The total charge inside is the volume, which is A times D, times 2D. It's 2D, A times 2D, divided by epsilon 0, and the volume must be multiplied by rho, which is the number of coulombs per cubic meter. A cancels, of course A cancels, nature couldn't care less how large you choose this A, and so you find the famous result that the electric field outside the plane equals rho times D divided by epsilon 0. And what the big surprise is, that it is independent of h. It doesn't matter how far you are from the plane, it's always the same. That's not so intuitive. In fact, if I had a surface which were modest in size, this is that plane, of course if I go very, very far away, the electric field here must be smaller than the electric field here. So why then do we not find that? Why do we find that the electric field is independent of the distance to this plane geometry? I want you to think about that a little bit. I want to help you though. I think it has to do with this absurd geometry, namely that we have assumed that our plane is infinitely large. Give that some thought. So now you have to do the electric field inside. I will only start you off on that, but no more. So here is the slab, and here equals x equals 0. Now you can either choose a box or you again can choose a cylinder, but the cylinder now has to be completely inside the material. This distance now is x, and this distance now must again be x. You're going to calculate now the flux that escapes from this surface and the flux that escapes from this surface. There is no flux escaping from the vertical surface. And you are now going to put that equal to all the charge inside divided by epsilon 0. And you will find an electric field which now linear with x. It turns out that it is 0 at x equals 0, and it grows to a maximum value at this point, and that maximum value at this point E, no surprise, will be rho times d divided by epsilon 0. But I would like to leave you with that. It's an interesting exercise, and as I said, I need a lot of time for the last problem.